Welcome to lecture 6. So in this lecture, in this part of the lecture, we're going to start looking at Erner models without replacement. Now, this is going to follow a very similar procedure to what we did in the previous lecture. So, let's just get into it. So we've got an urn, which contains n balls. Okay, and from here we draw little n balls. But now without replacing them. Okay, so as we had before, we're going to start with a lot of information and we're going to suppose that every ball has an individual label. So label the balls from 1 up to n. Okay, well then the sample space that we're going to consider, which we're going to denote as this, the little not equal, is, it's the list of labels that we draw out in order, where omega I is not equal to omega j, for I not equal to j. Okay, in other words, we only pick label, say j, or say we only pick each label at most 1 times in here. If little n is big N, then we're picking each label exactly once, and then we're looking at how we can order the choice. Okay, and we're going to which we equip with the discrete sigma algebra. Okay, and we're going to just assume that every ball is equally likely to be drawn. So that means we're going to equip this sample space with this sigma algebra with the uniform distribution again. Okay, so we're going to denote this little row arrow, and row arrow as the distribution, the density of the uniform distribution here is going to be, by definition, it's 1 on the number of elements in this set. And how many elements are in this set? Well, for your first choice, you have capital N choices to pick from. For your second choice, you have n minus 1, and you keep going, and you end up with n minus n plus 1 on your nth draw, and then we stop counting. So this number in the denominator is the size of omega bar not equals. Okay? So, that was pretty easy. We figured out the probability of each individual draw coming from here. Now we're going to do what we did previously and map this to throw out information. Okay, so suppose that we're not interested in the order. Okay, so we want to drop the order. One way you can do that is use this sample space, which will denote omega tilde, and this is going to consist of subsets of 1 up to n, which have n elements in them. Okay, so note here, this may get a bit confusing. This omega tilde, the elements here, so the points, your outcomes, which we're modeling with this, are really subsets of 1 to n. So subsets of this are going to be a collection of subsets of 1 to n. Okay, so we need to be a bit careful here, just we don't get ourselves confused. And how does this set model that we've dropped the order and that we're drawing n elements? We're saying that omega tilde, little omega tilde, is a subset of here. Subsets inherently don't have an order on them, and they also don't have you don't count duplicates of elements, and then that there are n draws is sort of captured by this. Okay, well, what's the push forward measure? Well, first of all, what's a random variable going between them? So we consider y, which goes from omega hat not equals to omega tilde. And what should it do? It should take a sequence of draws and map it to the set of draws. Okay, so by saying it's a set now, we've dropped that we're looking at it with an order. Okay, and well, let's calculate the push forward. Well, sorry, I should mention this, because we're equipping everything with the discrete sigma algebra, this is automatically a random variable, so we can use it to push forward our uniform distribution on omega bar not equal. Okay, so let's figure out what that is. Again, we can just do it on a singleton. So we're going to equip omega tilde with this measure p tilde. We're going to look at it on a single element of omega tilde, and this, well, it's u omega bar not equal of the set y equals omega tilde. Okay, which is just the size of the set y equals omega tilde divided by the size of omega bar not equals. Okay, now how many elements are in here? Well, elements of y have order, and when we throw that out, we sort of, well, to move between different elements of ordered sequences that have the same collection of points as here, there are going to be n factorial sort of different ways of ordering these. So this numerator is n factorial, and the denominator, which we figured out earlier, was n times n minus 1 times n minus n plus 1. Okay, and well, this is the same as sort of doing some algebra. This is 1 divided by the multinomial distribution of this. But if you work a bit on this, you'll find that this denominator here is exactly the size of omega tilde. Okay, which means that, which means p tilde is uniform on omega tilde. Okay, this is a nice coincidence, but perhaps you could do some reasoning and figure out why this is reasonable. Okay, so at this point we've gotten to unordered samples. So we've ignored the order, but we're still looking at all the labels. The next thing we want to do is to throw out the labels and only consider colors of the balls. Okay, so ignore labels. And this is very similar to what we did previously. So we consider E set of colors, and for all A in E, a subset CA of E. Oh, not of E, sorry. Of the labels corresponding to color A. Okay, and we let NA be the number of balls of color A. Okay, so this implies that N is the sum over the different colors of the number of balls. Number of balls of each color. Okay, and well, now there's one option of sample space we can use, which is exactly what we used when we did have replacement. So we're going to let omega hat be the set of, well, Ka with A and E in Z plus to E, such that the sum is equal to N. Okay, now just looking at this straight away, you could think maybe there's something very weird going on because, well, suppose we only had, say, 3 blue balls and 2 red balls, and say we draw 4 balls. Well, then an element of here is going to be, well, 4 blue, 0 red. Okay, but this is not a possible draw when we've only got 3 balls and we're not 3 blue balls and we're not replacing them. Okay, but it turns out, just because of how the push forward measure works, singleton sets that contain sort of events which aren't hit are actually going to be assigned probability 0. So it's perfectly fine for us to work with this sort of seemingly too large sample space. Okay, well, let's figure out how to sort of the random variable we're going to use to push forward. So we're going to have some t from omega tilde to omega hat, and it's going to do, well, what it should, where t of omega tilde is equal to omega intersect CA A in E. Now let's just check that this makes sense. So we've said that omega tilde consists of subsets. So this omega tilde consists of subsets of omega bar not equal to of size n. So, and, oh, sorry, that's not correct. It's not of, sorry, let's just go back and have a look at what it was. Yeah, no, subsets of 1 to n. Subsets of 1 to n of size n. Okay, and CA is a subset of here as well. So this is really just counting how many labels that correspond to color A are in omega tilde. Okay, so this is what we want. Okay, with everything equipped with the discrete sigma algebra, we can note that this is a random variable and construct the push forward of the measure we had previously, and we'll denote that by p hat. And we find applied to a singleton vector, this is uniform distribution on omega tilde pushed forward via t of the singleton. Okay, which is uniform of t equals k bar, which is size okay. Now, well, let's figure out the size of this set. Okay. So, how many omega tilde in omega tilde get mapped to k? Okay. Well, there are Na balls of each color. And we want to choose Ka of them. Okay. And, well, we've seen how to do that previous, or no, maybe we haven't, but, well, the way that you would do that is for each color, so it's going to be a product over the way that we can select each color. We're going to have, well, you want Na balls, you've got Na balls, and you want to choose Ka of them to be included in omega tilde, and so the others to not be included. So you would have Na choose Ka, Na minus Ka. Okay, so this is the size of the set t equals k. All right, and then, well, putting it all together, we find that p hat of k, of the singleton set containing k, is the product over A in E of Na choose Ka and divided by N choose N minus N. Okay, and we give this a name. We call this the hypergeometric distribution. Oh, sorry. We call this the hypergeometric distribution for n choices with n. So this would be all the list of the NAs. Yeah. Of K. Okay, so yeah, this stands for hypergeometric distribution. Okay, now I have been a bit sort of pedantic here in that I've been writing our multinomial distributions everywhere, even though they're really binomial distributions. So I don't think I made this particularly clear last time, but if you've got a multinomial distribution with only sort of a two-dimensional vector in the bottom, then that's always going to be of the form n and sort of k, n minus k, because the bottom two have to add up to the top one. We're going to just, instead, this will normally be written as n choose k, and this is your usual binomial coefficient. So sorry about making things a bit complicated notationally elsewhere. But yeah, just as I mentioned in the previous lecture, be careful that this is in general. In this course, we may have the bottom here denote a vector or a list of integers, in which case you need to be careful that it means by multinomial distribution. Okay, and to that effect, well, we can look at the hypergeometric distribution if you've only got two colors. So suppose E is just a color 0 and 1. Okay. Yeah, well, that means you're going to be choosing sorry. Oh, yeah. Then, yeah, so suppose you've only got two colors and you're drawing n balls. Well, then you've really got to draw sort of k balls of one color and n minus k balls of the other. And in that case, this hypergeometric distribution simplifies a bit. So you find there's going to be h of n, and then there's going to be, well, there's n minus n1 balls of color 0 and n1 balls of color 1. And this on, well, you're going to have k of color 0, n minus k of color 1 is really the same as, well, just manipulating the formula above, n minus n1, n minus k. Sorry, that should be k times n1, choose n minus k, divided by n, choose n. For, well, k has to be between 0 and n. Okay, so yeah, just as we saw previously, things simplify a bit when you only have two colors. All right, we're going to compare this hypergeometric distribution that you get when you aren't putting the balls back to the multinomial distribution we got last time where you do put the balls back in the next part of the lecture.